Hello everybody, this is Mohammed Abdulaziz. I'm from Technical University of Munich. Today I'll be talking about joint work with Dominic Berger, who was one of my bachelor students. In particular, this is about a new algorithm to compute upper bounds on plan lengths. So in this work we consider computing a quantity called the recurrence diameter of state spaces of planning problems, and using that to compute upper bounds on plan length. So first of all, I want to define what a recurrence diameter is. So given a directed graph, the recurrence diameter is the length of the longest path in the state space in that directed graph that does not traverse the same vertex twice. So it is the longest path, the longest path that only traverses the same states. The complexity of computing the recurrence diameter for an explicitly represented directed graph is NP hard. So that's a problem. So it can have bad running time for practical algorithms. So in this work we explore how to compute the recurrence diameter for planning problem state spaces while and how to do that in a practically useful way. So the reason we do that is that we need computing recurrence diameters would improve if we have a practical way to compute recurrence diameters that can improve the upper bounds a lot on plan lengths, and this in turn would improve the performance of site-based planning algorithms that use these upper bounds on plan lengths, either to find plans more quickly or to prove that a certain planning problem does not admit a solution. So the challenge for this, the challenge is not that the running time, that the complexity of computing the recurrence diameter is only NP hard. It is indeed non-deterministic exponential hard for succinct directed graphs like state space of strip spanning problems. What that means is that computing the recurrence diameter can actually take a doubly exponential worst case running time in the size of the given planning problem. So we solve that challenge by two contributions basically. The first one is we devise a better encoding into SMT formulae, and we basically encode the question of is a certain number the recurrence diameter of a planning problem into a small SMT formula. So just to be quick here, so the only previous encodings for recurrence diameter, the first one was invented by Alain Biere since 1999 when he invented bounded model checking, and since then it didn't really improve much. And the problem of that encoding is that it builds the entire state space and then produces a formula whose size is quadratic in the size of the entire state space, so it can be exponentially bigger than the given problem. Our encoding has the advantage that the formula can actually be only quadratic in the size of the given planning problem, so the quadratic in the size of the factored representation, and thus it can be exponentially smaller than the formulae by Biere. We also, another contribution is that we devise a method that shows how to practically compute the recurrence diameter, and only for projections that are small, for projections of planning problems that are small, and for other projections that are bigger, we compute other bounds other than the recurrence diameter, and then we show how to compose these bounds for a given planning problem into a bound on the whole problem. So a given planning problem is divided into abstractions. Small abstractions we compute recurrence diameter, bigger ones we compute other bounds. So as you see here in the experiments, the bounds computed when the recurrence diameter is involved are much tighter than the ones when it's not, as it's shown in the left figure. But the problem is that bounds computed with the recurrence diameter take longer than bounds computed with other algorithms. But as shown on the right plot, the overall running time of planning, including the running time for computing the upper bounds, still is much better when you use the recurrence diameter, because the bounds are are very tight that it eventually pays off. Thank you very much. If you have any questions, please email me. Thanks.